Okay, we're going to prove that the Cantor set is uncountable. So this is the theorem I mentioned in the Cantor set video. And just as a reminder, completely optional. This is not required for our course. We're not going to have any associated exercises, just for fun. So the Cantor set is uncountable. And again, this is a fairly remarkable result. Right, the Cantor set is obtained by repeatedly removing pieces of the interval 0, 1. It looks like we remove quite a lot, but it turns out the set is an uncountable one. So how are we going to do this? So we need to talk about ternary numbers, which are base 3. So let's talk about decimal numbers first. So this is base 10. And this is really what we're used to, right? So let's say that we have this, n is, let's write it in this way. So a sub m minus 1, all the way down to a2, a1. And these are digits. And what that really means then is that n is 10 to the m times that mth digit, plus 10 to the m minus 1 times the am minus 1 digit, and so on. Oh, I guess I should have, sorry, this should have a 0 on it. All the way down to just 10 to the 1, a1 plus a0. Right, so we have this idea of this is the ones digit, the tens digit, and so on. Okay, so in ternary, we just switch this to base 3. So all those powers you see there, so ternary numbers, this is base 3. Okay, so when I write something like this, n is, say, b sub r minus 1, all the way down to b sub 2, b sub 1, b sub 0. Here, everything's powered with 3, so it's 3 to the r times that digit b sub r, plus 3 to the r minus 1 times b sub r minus 1, all the way down to 3 to the 1 times b1 plus b0. And so instead of ones, tens, hundreds digits, it's ones, threes, nines, 27. So it's all powers of 3 instead of powers of 10. So this is the ones digit, this is the threes digit, and then so on and so forth. Okay, so for example, let's say we have and the digits are only so the only digits are 0, 1, and 2. So for 10 you get the digits 0 through 9. For base 3 ternary you get the digits 0 through 2. Okay, so let me just make that note too. So the only digits are 0, 1, and 2. Okay, so for example, if I had the number 2, 0, 1 written base 3, so this is what tells me that subscript 3 tells me that I'm working in base 3. Then this should be 2. Oh, sorry, not 2. So this should be that's the 3 squared place. So that's 3 squared times 2 plus 3 to the 1 times 0 plus 3 to the 0 times 1. Okay, so we're looking at 9 times 2 plus 3 times 0 plus 1 times 1. Okay, so this is the number 19 written in base 3. It's 201. Okay, so that's how base 3 works. And now let's talk about decimals, and then that'll bring us to the Cantor set. Okay, so to get to the Cantor set, we need to talk about fractional ternary numbers. So instead of decimal places, we'll be talking about ternary places. All right, so fractional ternary numbers. Let's say we have something base 3 written like this. So it's 0.C1, C2, C3, C4, and this number is base 3. So what do these places mean? In decimal places, we have one place referring to the tenths, another place referring to the hundredths, another referring to the thousandths. Here, it's 1 over powers of 3. So this is the 1/3 place. Over there. C2 is in the 1/9 place. C3 is in the 1/27th place. And so on. Okay, so that's how we deal with fractional ternary numbers. Again, the only digits are 0, 1, and 2. Okay, so for example, yeah, okay, so let's do this. So I want to make this comparison between decimals. So this is base 10 here. If I wrote something like 0.0999 recurring, okay, just nines forever, that's equal to 0.1. Those things are the same. In ternary, we have a similar thing. The highest digit is 2, remember? So if we had 0.0222 recurring, just 2's forever after that, that's also equal. That's going to be equal to 0.1 in ternary. All right, so that's something that's important to remember. So what does this have to do with the Cantor set? Okay, so constructing the Cantor set. Remember, we start with that interval from 0 to 1, and then we remove the middle third. So what we're left with is 0 to 1/3 and 2/3 to 1. I want to think about what these look like as ternary numbers. Okay, so here's the thing to think about is that in base 3, these numbers are all less than 1/3. These numbers all start with 0.0 and then something comes after that. Because 0.1 in ternary is 1/3. So we're less than that, so we need to start 0.0 and then things coming after that. Now remember, so yeah, just as a note, 1/3 is 0.1 in base 3, and 2/3 is 0.2 written in base 3. Okay, and so that means that these numbers here these all start with 0.2, and then there are digits that come after that. Okay, but what about in the second step? So what's happening is in the first step, we remove all base 3 numbers that have a 1 in the second ternary place. Right? I remove that middle, and that's what corresponds to numbers that begin 0.1 and so on in ternary. And then we're going to remove more. When we remove more middle thirds, you can check on this. This just jumps to the next place. We're gonna remove all the base 3 numbers that have a 1 in the. Oh, sorry, I wrote the wrong. This is first. In the first ternary place. In the second step, that's when we'll remove all base 3 numbers that have a 1 in the second ternary place. When we remove the next middle thirds. With 1 in the second ternary place. Okay, so the upshot of this is the following. So the Cantor set is all numbers that in base 3 have the form 0 point something with only 0s and 2s. Okay, so that's what the Cantor set is. When you switch to ternary numbers, base 3 numbers is it's any number of the form 0 point anything you want. But that string of ternary digits has to be only zeros and twos. We can't use ones. Removing all the ones is equivalent to removing all those middle thirds, which is how the construction goes. All right, finally we're ready for our proof that the Cantor set is uncountable. We're going to use Cantor's diagonalization argument here. So again, proof. Again, the result is the Cantor set is uncountable. Okay, so suppose the Cantor set is countable. And write an ordered list of all numbers in the Cantor set in base 3. Okay, so I want them in ternary. Okay, so I want them in base 3. And we're just going to construct a number that is not in the list but has to be in the Cantor set. So this is how we'll do it. Let A be this number. So it has its point T1, T2, T3, T4, and so on in base 3, ternary, where each digit is defined as follows. T sub I, so this should look very familiar, is going to be 0 if the ith ternary place of number I in the list is non-zero, or I should just say 2. There are only zeros and twos that are appearing here, right? So I'm just going to say if it's 2, put a 0 there, and it's 2 if the ith ternary place of number I in the list is 0. And that's it. That's all we need here. And then our number A is definitely in the Cantor set because it has this form, 0 point, all these ternary digits that are only zeros or twos. And it's not on the list because it differs from the ith number in the list in the ith ternary place. So A, we know A is in the Cantor set since it is of this form, 0 point something, all twos and zeros. Right, again, base 3. And it differs from every number in the list. So it's a number in the Cantor set that's not on the list. This is a contradiction. And so the Cantor set must be uncountable. Okay, great. So there it is. Again, if you want to talk about this more, I'm happy to do it, but it's just Cantor's diagonalization argument again. You just have to switch the base of your numbers to be base 3, right? Ternary instead of decimal. But once we do that, there's a really nice description of what the numbers in the Cantor set look like, and then we can use that to our advantage to come up with this proof of uncountability.